The legs of an isosceles right triangle increase in length at a rate of 4 meters per second. To answer this question, I'm going to draw a simple diagram, and that is an isosceles right triangle. So a right triangle where these two sides, the legs, are the same length. And we're asked to use the variable x for that length. Since we're told that the legs are increasing at a rate of 4 meters per second, that's how fast this side and this side are increasing. In terms of derivatives, that's the derivative of x with respect to time. And I'll put 4, and we'll just note that that's meters per second. Part A asks us to write an equation relating the area to the length of the legs x. Since the area for a triangle is 1/2 the base times the height, here the base is x and the height is also x, so base times height will be x squared, and this is the formula that we are asked for. Area is equal to 1/2 x squared. To complete this part, we need to take the derivative of both sides of this equation with respect to time. And this will allow us to relate the rate at which the area is changing to the rate at which x is changing. So to do this, if we start with a, the derivative of a with respect to t is simply dA dt. I'm going to do the same thing to the other side of my equation. We have to use a rule here. To take the derivative of x, I'll take this 2, bring it down front, multiply it to the 1/2, and 2 times 1/2 is equal to 1. I won't write that. I will copy down the x, and I'll subtract 1 from the exponent. I won't write that either since it is 1. But you get something else here. By the chain rule, you have to multiply by the derivative of x with respect to t. So here we have a formula that connects the rate at which the area is changing to the rate at which the sides, the legs, are changing. And that's what we're supposed to enter in here. Now to continue, it asks, when the legs are 1 meter long, the area of the triangle is changing at a rate of, and this is where we're going to go directly to this formula here. We're going to take 1 for x, we'll put that here. We were given dx dt is equal to 4, I'll put that here. And when we multiply together, that's going to be the rate at which the area is changing. So I will include the units in this part just so we can see how it works. But dA dt is equal to, well, x we're told is 1 meter. The rate at which the legs are changing is 4 meters per second. So the answer is going to be 4, and the units are meters times meters, which is meters squared, and that's per second. And that's what we're supposed to enter here. So, not only is this formula true, but when you plug in the units, it should be that for an area, we don't have meters, but we have meters squared. So everything seems to match up here. For part B, kind of similar to this part of the question here, but it says, now when the hypotenuse is 1 meter long, so when this length is 1 meter long, how fast is the area of this triangle changing? So we're told that, I'll call h the hypotenuse, we're told that it's 1, and our formula does not depend on h, it depends on x. So this means, using this information, we'll have to solve for x. I'm going to do this by using the Pythagorean theorem. The square of this side plus the square of this side is equal to the square of this side, which we're told is 1. So I'll write this off to the side, but we're told, okay, if we square both of the legs and add them, that is equal to the square of the hypotenuse. We have 2x squared is equal to, well, 1 squared is simply 1. And if we solve for x, we would divide both sides by 2. And then take the square root of both sides. Because x represents a length, we'll only take the positive square root, so that's the square root of 1/2. And, well, you can break apart this square root to 1 over the square root of 2, And if you rationalize the denominator, you could write this as root 2 over 2. So really, either of these values are okay. I'll choose this one to represent the length of x. I can now figure out part B. I'm going to put this value here to get my final answer. So we have that for part B, dA dt is equal to, okay, this is root 2 over 2 meters times our given dx dt, which was 4 meters per second. And when we multiply these values together, all right, well, this 2 goes into that 4, leaving us with a 2 left over. We still have a square root of 2, which does not cancel, so I'll include that. And again, we get units that are meters squared per second. So that is going to be the answer for part B. Exactly, it's 2 root 2 meters squared per second. And finally, for part C, it says, write an equation that's relating the length of the legs of an isosceles triangle X to the length of the hypotenuse, H. Now, we can do it using this formula. So instead of just using 1 and putting it here, we could have left this 1 as the variable H. Running out of room, I'll put that on the next slide, but essentially, we're going to get a formula connecting X to H. We're going to take its derivative to then figure out, well, how does the rate at which H changes compared to the rate at which X changes? So we had that in this isosceles right triangle, x squared plus x squared is equal to h squared, or 2x squared is equal to h squared. This is the formula. But what we need to do is take the derivative with respect to t of both sides of this equation. That way we'll get a dx dt and a dh dt that we can relate to one another. So starting with this side, if I take the derivative with respect to t, this 2 comes down front, making this a 4. I'll copy down the x. I will subtract 1 from the exponent, which I won't write because it is 1. By the chain rule, I have to multiply by the derivative of this thing with respect to t, dx dt. Very similarly, on this side, I bring down the 2, copy down the h, subtract 1 from the exponent, but now I'm going to multiply by dh dt. So this thing was the original equation, and this, it's not simplified, but this thing is the formula connecting dx dt to dh dt. I'm going to solve for dh dt, the rate at which the hypotenuse is changing. Well, for starters, I see I can cancel a factor of 2 from both sides. So this is really 2x dx dt is equal to h dh dt. And I can divide both sides by h, which will put it in a denominator that I'll write over here. I'll put 2x divided by h. So that's 2x over h times the rate at which x is changing is equal to the rate at which h is changing. Given information again from this problem was that dx dt was equal to 4. So we really don't even need this symbol anymore. It's a constant rate. It's equal to 4, which when I multiply to this 2 makes it an 8. So just a reminder, we were told that this is always 4. And when I multiply that 4 to the 2, this whole side becomes 8x over h. And it looks like, maybe this is where it ends in terms of simplifying it. However, I bet we can write this in terms of either just x or h. The way you can do that is by going back to this equation. We have an equation that connects x to h. Maybe if we solve it for h, it'll be in terms of x, and I can plug that information in right here. So let's do that. Okay, so we have that 2x squared is equal to h squared. I could have taken the square root of both sides of this equation. Since x and h represent positive values, the right side is really simple. It's going to be h. On the left side, it'll be similar. When you take the square root of x squared, well, this first part will simply be x. But when you take the square root of 2, it doesn't simplify, but root 2 is a number, and so you can put root 2. So, here's a simpler equation that connects x to h. The point of that was, well, if these two things are equal, and here I have h, why not replace it with root 2x to make this side more simple? So to do that, I will take, again, we have 8x. I'll divide it by root 2x, and that's going to be equal to dh dt. And again, here we have stuff canceling. X cancels. We're left with 8 root 2 is equal to dh dt. Also, we could rationalize the denominator. You can multiply the top and bottom by root 2 and root 2. In your numerator, you'll have 8 root 2. And in the denominator, root 2 times root 2 itself is just 2. Kind of a long way to go, but 2 goes into 8 4 times. I mean, this looks like the completely simplified answer where, you don't have a root in the denominator. But it turns out, since dx dt was constant, it was 4, the rate at which it changes was always the same number. Same thing is true for the hypotenuse. It's always changing at a constant rate. I mean, it's different than this value, but it was equal to 4 root 2. And that is the final answer for this problem.